Our next speaker is going to be Kevin Kung, and Kevin is going to talk about biomass torrefaction for high-yield water-saving fertilizer. Kevin.
Good morning. My name is Kevin, and I was here as a PhD student in the mechanical engineering department for 4 years with Professor Gongning. And now I'm a cyclotron rail fellow based in the Lawrence Berkeley National Lab to continue the commercialization of this MIT technology. So what we do is that we use MIT-developed technology called biomass torrefaction to enable small-scale decentralized production of fertilizers in remote areas. So one of the problems that we are trying to solve today is that a lot of the fertilizers being produced today are done in a very large scale, centralized, and capital-intensive facilities in places such as Morocco, Europe, and North America. And then you ship that fertilizer to rural places such as Africa and South Asia. And because of this long distance transport and logistics, a lot of the farmers in rural area actually pay 2 to 3 times the price than the rest of the world on their fertilizer. And for them, because a lot of these farmers have very limited amount of income, they often only rely on the cheapest synthetic varieties that over the long term can actually degrade and acidify their soil. This actually is a pretty big problem. In the worldwide, we estimate that farmers typically spend about $30 billion a year on ineffective or partially effective fertilizer that ends up degrading their soil. So the concept of what we're developing here is that we try to miniaturize and decentralize the fertilizer production such that it can be implemented on a village level on a profitable basis using locally available resources, labor, and materials. And this process is based on hardware technology. So imagine small-scale, low-cost portable equipment that can be latched onto the back of tractors, donkey carts, shipping containers, and that can be brought from farm to farm on site to essentially process the locally available residues, the farm residues after harvest, into an intermediate for the fertilizer. And that's something that we enable. And the process looks like this. So right now, in many rural areas, there's a lot of the agricultural residues, such as rice husks, corn husks, and pine shavings, and so forth. And what we can do with this is that we can actually use the torrefaction process, whereby we are treating these residues to a medium heat under oxygen lean conditions, which means low oxygen. And what that does is that it becomes this carbon-rich intermediate that's often called torrefied biomass or biochar. And then that's mixed with a binding as well as nutrient recipes to complete the nutrient, and finally packaged and sold as a standalone fertilizer. We can vary the condition of the reaction to produce fertilizers of different qualities and characteristics that are suitable for different soil, and in some cases may even achieve this targeted, customizable fertilizer on a single farm granularity. So this is something that we have been building a lab-scale reactor at MIT to test and validate. And after some success with it, we have also scaled up the production to about 10 kilogram per hour on a continuous basis. And right now, we are actually in the midst of commercializing this and setting up a village-based pilot. So how this looks like is that right now, we have a pilot in Kenya where smallholder farmers, instead of burning their crop residues and generating pollution, now has the option of using these preliminary equipment that we developed to turn it into something that they can sell to what we call a mini plant operation. These are the local fertilizer operation that can serve a radius of about 10 miles or about 1,000 farmers. There, it's added to these recipe blend and then processed at a margin into a safi-sarvi, which is a fertilizer that's then sold back via the existing distributors or agrovets in the village back to the same farmers, and thereby achieving this waste to nutrient loop. This is something that we've been piloting for the past 3 years, and we have acquired 2,500 farmers as paying customers, and the local team has grown to 10 full-time employees, and in the last month, we actually just reached financial break-even point with this pilot operation. And as we scale this, next step is that we want to really build a continuous prototype into this equipment and showing how we can move the operation towards higher profitability. So with that, I will end. We have a poster here. Please feel free to come by and ask any questions. Thank you very much.